Hello and welcome from Oslo to this webinar that we will today host on solar energy and the solar industry revolution and the impact it has on wireless communication. There's still some people joining, so I will just wait a couple more seconds before I start the formal presentation. I hope you're doing okay around the world today. It's a sunny day in Oslo, so it's a good day here and just 2 days until the weekend. So we're looking forward to that as always. I think I'll just be starting. There is energy crisis in the world, and that's combined with also an environmental crisis. So the need for renewable, sustainable energy has never been bigger. And there's being done huge investments all over the world, in Europe, in Asia, in America, on renewable energy. So that's wind, that's solar, that's the hydropower. And with the energy crisis which are here, we are seeing energy pricing go up very high. And that makes also these renewable energy resources or sources very profitable. So in light of that and all the investments done and funded by, which is also funded by the government, we see a revolution in these industries. There is, as I said, huge investment. The EU alone is planning to double its solar energy, available solar energy by 2025, and even increase it more to 2030. This is the backdrop of today's presentation, and that's the kind of importance of what's going on in the world. And this is why we also want to focus on this segment. Just some practical things. With me today, first of all, I'm Ørjan Nottveit, the R&D Director of Radiocrafts, and I'm very happy to be joined today by Fritjof Engelhardtsen, which is the technical manager in Radiocrafts, who has been working a lot with our customers in the solar energy industry. We will have a webinar which is planned to last 30 minutes, maybe it's slightly less, and then we have some time at the end available for Q&A from the audience. You can post your questions in the chat window, and we will take them after the presentation, so not during it. This webinar will be recorded, so there will be a recorded version on our webpage that you can download and look at later, or you could share with your colleagues or something like that. Also, if you want more detailed information about our solar energy solutions, you can visit our webpage to find more detailed both white paper and application note for this market segment. So, of course, solar industry is not something new for us. We have been having customers in the solar industry for many years. So maybe you, Fritjof, can share a bit about how we got into this solar industry.
Well, I would say it was rather that the customers came to us without actually us doing much. You know, we provide the radio solution for many different segments. But, you know, we started noticing that there was an increasing trend a couple of years ago that we had customers coming to us for solar-related applications. And so maybe a year ago, we decided that we wanted to get a better understanding of the solar industry and really try to learn a bit more about this segment. And so we decided, for instance, to participate at Intersolar this year as part of the Norwegian Pavilion. And there we got the chance to talk with both existing customers and also new customers in the solar industry. So a lot of the things we're going to show you today is kind of you know, what we have learned, you know, digging into the solar industry and trying to get a better understanding of this. So what is really solar industry? For me, it makes sense to separate this into three different segments. So we have the really large installations, and this is typically called utility scale installations. It's large installations out in the fields, out in the desert. It's many devices, can be thousands of devices. Solar trackers that enables the solar panels to follow the sun during the day, so their angle is optimal. Then we have this kind of medium-size installation that is quite large, but still not as large as the vast installations out in the desert. And these systems are typically up on the rooftops, I would say. So we call this medium-size segment rooftop and industrial segments. And then we have, the residential segments, and these are basically a single household or a few households that have solar panels on the roof, maybe some energy storage system, maybe some EV charging system as well as part of the system. And I think it's interesting to see some differences between the systems, and it's really down to the grid codes. So the grid codes, they define how these installations interface with the public electricity grid. And the larger the installations are, the stricter the requirements are defining exactly how these installations should feed energy into the grid, and how they should adjust their output and stuff like that, so you don't overload the grid and stuff like that. So that is an important distinction between these systems. I also think it's very interesting that some EU regulation now mandate solar installations on certain new buildings. I think that is going to really increase the number of installations, particularly the rooftop and the residential size installations.
So do you see the trend, Fritjof, when you talk out at Intersolar and talking to customers? Are we going more towards the residential and smaller, or are we kind of seeing growth in all these segments?
So I would say that we see growth in all of these segments, and we do have customers in all of these segments today. There's slight variation about requirements and the system the configuration that is able to meet requirements, but in general we see equally good uptake in all of the segments.
Okay, very interesting. I guess it's we need more energy, so we need it from all. all have to participate, kind of, to create enough renewable energy. You talked about a bit of these different. You talked about the trackers. You have the controllers. Of course, we have the panels themselves, which everybody can see. So I guess all these solar energy systems have a certain number of devices and with different tasks. So I know that we have been discussing this a lot, Fritjof. But maybe some of the customers want to have a better understanding of some of the listeners need a bit of update on how on what type of devices are in such a system and what their different job are. Yes, then I managed to make the next slide.
Yeah, so we try to make a figure here showing the kind of components that you will commonly find in this type of system. And, not all of these components are present in all of the segments, but many of them are. And, it all starts with the solar panels. So here you see solar panels that are connected in series, and they are fed. They feed their DC voltage then through a device called a DC combiner. So a DC combiner basically takes a series of solar panels, and when you connect these solar panels in series, you get a higher DC voltage that then is fed into an inverter. I think it's interesting here that the DC combiner is then able to monitor the solar panels. A DC combiner is particularly used on the large utility scale installations. And it is able to detect such things as, for instance, the physical degradation that can happen with the solar panels over time. In some cases, the solar panels will actually feed the DC voltage directly into the inverter. So there can be some variations of this architecture. Then you have the inverter, and the inverter is then taking the DC voltage and then generating AC main voltage. And this main voltage is then fed into the electricity grid via electricity meter. I think it's also interesting here to see that you have a very central device in all of this architecture is what is called a power plant controller or a data logger. So for the really large installations with many inverters and many DC combiners, this will typically be called a power plant controller. And it's called the controller because it is also sending control commands to the inverter so that they will adjust their output according to the needs of the electricity grid. For the smaller sized installation, this is more often called a data logger because it is more about trying to log and create statistics about the energy generated by your inverter, and that you can, detect the failure of one of your inverters. On the really large installation, there is typically a connection or an API between the grid operator and the power plant controller. So this allows the operator of the public utility grid to send commands to the power plant controller so that they can adjust the output of the inverters to meet the needs of the grid. So that, for instance, if you have too much renewable energy generated, then the grid operator may send a command to the power plant controller for it to reduce the output of the inverters. And this communication will typically have some latency requirements. This should happen rather quickly for the inverters to adopt, so we don't get critical situation that you burn up the grid because you have too much electricity fed into the grid. On the really large installations, you also find a lot of other devices. There can be weather stations out there. There will be solar trackers that position the angle of the solar panels correctly towards the sun. There can also be devices like aerometers here that will measure the amount of incoming sunlight. And there can be some devices measuring the angle of the trackers to make sure that they actually move accordingly. So it's really a rather large IoT system with a lot of communication going on. And then you have the energy storage. So you can also have a battery bank connected to the inverter. And this is can be for all of the sizes here. And for the residential and the rooftop case, we can also have EV charging points that connects to the system to support EV charging.
Interesting. And I guess all of these can be, obviously could be wired together, or can't they?
Well, so the case with the really large utility scale installations today is that they use a lot of cabling. So there's a lot of fiber optic cable loops and kilometers of cable, both electrical cable, RS-485 cable, and fiber optic cable that is dug into the ground in these large installations. But there is also use of wireless also. But, for all of this installation, there is really, many benefits of going wireless. We hear about problems, when people put a wire in the ground, even in the large installations, you have challenges with lightning strikes and ground loops. And when you have a cable that connects many devices, suddenly you will lose communication with the whole segment of the solar installation. And we also see that, you know, there is also a lot of cost involved with drawing all of that cable and making sure that the installation is done correctly. So, yeah.
Yeah, so now, of course, we do see that there is a, as you point out, that there's a need for, there's a requirement for wireless and there's interest for wireless, because it's specifically the installation costs of having these wires is tremendous. I mean, wiring a complete system could take days, I guess. So the flexibility and the ease of installation and thereby also the cost of installation is I guess one of the driving factors for wireless. And we also need to roll out many of these systems, so we need it to be smooth and efficient installation, all of it.
But Ørjan, you have been working closely with many customers in this segment, and can you share some insights into what kind of wireless solutions are suited for these kind of installations?
Yes, I can, Fritjof. As you say, there are many different wireless technologies, and here also you have outlined three different use cases, and then you have a lot of different equipment in each use case. So all of this creates different requirements. Obviously, if you have 1,000 solar panels you want to have connected to one controller in a utility scale system, 1,000 panels. Obviously, that would be a huge network and have slower operation, more delays, stuff like that, than a smaller, like, residential system. So it creates a set of different requirements. One of the key requirements that kind of the first we noticed is, of course, the requirement for range, because as you know, if you look at for instance, the residential case, you have the solar panels are outdoor on top of the roof, and maybe your battery pack is in the basement. So obviously, that also creates a challenge. The second, if you look at the rooftop installations, for instance, we see an example here. Often you have a controller which is 2 or 3 stories down in the building, 2 or 3 floors down, and then you have the solar panels, of course, on the roof again. So you need to make sure to reach up to the roof. You could have also, of course, in the utility scale, when you have kilometers of these, you need range, basically. So that often leads us to sub-1 GHz radio communication, which gives better range than 2.4. But also because, like the example shows here, you have solar panels on different rooftops. You need them to communicate, and you're not reaching the third roof here, because you only reach the first and the second one with your controller. You want typically multi-hop solutions, so you want mesh solutions to be able to make this scalable. So the combination of sub-1 GHz and mesh seems to be a very good solution for many of these cases. Basically, showing on the right is, of course, the advantage of sub-1 GHz and also the C1 one data logger communicating to one solar panel on the roof, and then having that one communicating with the different solar panels. So that range is kind of one, and then you have another solution which kind of contradicts range, and that is latency, because as you say, latency requirements, you have to kind of consider carefully what type of equipment you're communicating with. Obviously, if you're monitoring the weather station, you don't have to read it within 1 millisecond. The weather doesn't change that quickly. So obviously you want you can measure the wind and stuff every minute. That's more than enough, I guess. While if you want to set some if you see overvoltage in a network and want to adjust down inverters, and there are many of them, you want to communicate all that within maybe a very short time frame. So obviously we see that there are many use cases here which are very suitable for wireless communication, and then there could be some use cases, like if you have 2,000 solar panels in a utility scale, and you need to control them within 10 milliseconds or something. Obviously, you're into fiber communication or something like that. So you have to kind of look at what is it you want to do, and what type of requirements does that lead you to in terms of latency.
So Ørjan, you talked about latency, and in terms of what kind of solutions we offer. Do you see that that there is one solution that is suitable to all of these applications, or how can that be managed?
Yeah, as I mentioned, we have our sub-1 gigahertz mesh solution, mainly the IP mesh called RIM, which is suitable, and then in that network protocol, our users can do a lot of adaptation for the different systems themselves. So some want quick joining, some want low latency, some want many devices in the network. So all these can be tuned, or you can prioritize a bit in your settings of your network. And also we do quite a lot of work on customer-specific development, meaning that the customer wants something more than what can be adjusted in the network themselves. So they want it to be even, typically they come with us to us with their requirements, and we see, yes, this is possible, but we need to do this and this and this modification specifically for you. So we do a lot of that type of work as well. So it's customizable by the user, and of course we can then, in addition, to do even more customizing if the requirements are beyond the scope of what the system can do today. Yes, in addition to the range and latency, there's also the requirement for reliability. We are kind of replacing cables here, and cables normally work fine. Of course, they have wear and tear, which suddenly can get cable breakage, or you can have like sand in a connector or stuff like that. So they're not 100% reliable, but of course, in all wireless communication, you can lose a packet. So what we have been trying to do in our RIM network is see what is the best kind of technology to make a system reliable. And what is the kind of industry-leading protocol for reliability is to use what is called time-slotted channel hopping, or TISH as we call it for short, which is a protocol which enables you to send the message on different frequencies every time. So it's a frequency hopping system, which is very good for getting high reliability on a system. There's also a lot of academic research on time-slotted channel hopping. So if anybody's interested, they can Google it and find a lot of academic papers on showing how well it performs. In addition to reliability, there's another parameter which is often close to latency, and that is throughput. How much data are each kind of device generating? And again, weather station doesn't create that much data. A solar inverter can create a lot of data. This is more a system design choice. How much processing can be done locally at the inverter, at the solar panels? How can the data be filtered? How can it be compressed? But at the end, you end up with a certain amount of data that you need to get from each device. And if you only, for instance, transfer alarms, so it's kind of, it would be a requirement for low latency, but it will be very little traffic. So then probably your latency would be okay. But if you are having, I don't know, hundreds of bytes of data from each device every second, you basically can get congestion in the system because you have too much traffic. Also, one of the key elements of our RIM network is that in EU specifically, there's a challenge with duty cycle limitation. So when you start to transfer a lot of data, you will get a challenge that in EU with the red directive, you're only allowed to send for like 1% of the time. And that creates big problems for high throughput systems. So I don't know, in LoRaWAN, you have to kind of, if you're sending on a really long range, you have to wait 10 minutes between each packet, because otherwise you violate the 1% rule. So you need to kind of look into how much data and if you can get it through. What we have in the RIM network is that because we have the frequency hopping, or we use multiple channels, and we also monitor the channels to see which is the most noisy one. So we scan all the channels and find the most noisy one and remove them. So we choose to not use the most noisy channels. And in addition, when we send, we use a listen before talk, and combining those, the adaptive frequency agility and the listen before talk, we get something called polite spectrum access. And when we use that according to the red directive and the EU standards for wireless communication, we can send like almost 2% in each of the channels, and we have 14 channels, so that basically makes us send 37% of the time, and that's more than if you start to send each device send more than 30% of the time, then you will have congestion anyway. So this is kind of more than enough. So that's really one of the advantages of our RIM network for this adaptive frequency hopping.
But you have talked about how frequency hopping can increase the amount of data throughput we can manage. But what about interference immunity? How is that affected by, can you explain that for us?
Yes, so thank you for the question, Fritjof. Of course, if you have interference, can be many things. Interference could be other protocols like a Sigfox base station or a LoRa base station or something like that, which typically operate on kind of a single channel. And that means that we can, if we see that there's a lot of noise, we can kind of choose to not use that channel. So obviously that's a great benefit. But also because of this frequency hopping, pseudo-random frequency hopping, we will not be kind of if you talk about scaling, in utility scale, if you have 1,000 solar panels or maybe 10,000, they will not be in one network. You will typically have many different networks in parallel, but they're very close so if they were all operating on the same channel, they will interfere a lot with each other. And we have heard customers using single channel system which have huge problems with this. So obviously, the fact that you have frequency hopping and it's synchronized differently in the different network, you will have they will automatically kind of avoid each other. So they might have the same channel once in a while between the two different networks, but really we kind of solve the scalability issue automatically for the customer. So when you have many networks, so that's also a great advantage. Okay, I just want to summarize a bit here. We have talked about, or you presented, Fritjof, the different use cases with utility scale, rooftop, and residential. We also looked at the different devices with this power plant controller, which is obviously the key in all of these systems, but it could be different sets of devices depending on the use case. And then we have seen that the different equipment, the different use cases creates a lot of different requirements for communication, basically. And we see that many of these are well suited for wireless communication, because we have, and specifically our RIM protocol, which ensures the reliability they need, the scalability, and the range that they need. And then, of course, the latency, assuming that it's not many thousand devices in 1 millisecond, then obviously there will be a problem. But basically, for most of the cases, RIM is very well suited. So let's see if there are any questions here. Yes, we have one question here. Is the technology flexibly expandable? Communication and expansion must be very easy for cost reasons. Yes, it is expandable, but we do not recommend expanding one network, one radio network into, I don't know, many thousands. There's a limitation on 1,000 devices with our technology, but normally we don't even recommend 1,000 because bigger networks makes more hops and thereby also longer latency and stuff like that. But it's flexible in terms that we could have, if you have new devices, they can join any network, and we have quite good tools for automating the commissioning so that it kind of joins one network, and then the central unit can then guide it to where it wants it to be in the network.
I was thinking about Henry's question here, and one thing I think is very nice with the RIM technology is that the gateways, or what we call board routers, you know, they will automatically get their own unique frequency hopping pattern. So you do not need to basically do manual channel assignment on an installation. When you expand the network, you will automatically, you know, get a set of channels that have a small probability for interference. Isn't that correct, Ørjan?
Yes, it is. So that's a very nice nice feature. Going back to the questions here, I see there's a question from Vasilis who say, what range can be expected for RIM device, the low power variant, in urban areas and the open field? Of course, the devices come in, just to explain that, it comes in two different power variants. We have one which is 14 dBm, which is what is called the low power one, and then we have a high power one which can deliver up to 27 dBm or half a watt, which of course creates a longer range. A RIM device in an open field, if you go out of the city, in urban areas, there are two things. Of course, there are obstacles, but there's also more background noise. So there's two things. If you go in an open field and it's not in a city, I think you can get like 1,500 meter range, or maybe if you have a high antenna, you can probably get even longer. Yeah, actually you can quite much longer, I believe. In a city, I think you can get. Of course, it depends on how much buildings it is between. But if you find a open, if you can have an open like street or something, and down the street you can easily get 1,000 meters also in a city. But if you have a lot of buildings in between, maybe you have more down to 200 meters. But of course, for the solar case, we do recommend that you typically on the gateway raise your antenna a bit so you get above the solar panels. That's also always a smart thing to do, to raise the antenna in the central point to make sure that because all the solar panels of course creates a lot of reflections, so you want to make sure to make a smart positioning of the antenna so you don't make it more difficult than it has to be. We also have a question here from Caesar, and that is only big systems for company groups is listed in the PowerPoint. Is there an example for home use? Yes, we do have customers doing this for more residential use cases. Of course, it's smaller networks, but example for home use. I'm not quite sure what the question is, but yes, we do sell this system also for home use. You typically have one point in the electricity meters where you read what's happening there. You have one point. You have a microinverter, I guess, is normal for residential use cases, and so you can monitor the inverter and typically the energy storage, and also possibly the electrical vehicle charging point. So typically you have networks of maybe 10 devices. I'm not sure how many sensors. Is there any more sensors in such network, Fritjof? Have you seen what the customers are using there?
I would say that the networks are smaller, but you do have a lot of communication in this network. So you have frequent communication, and so it's really a benefit there to have the adaptive frequency agility. I would say in Europe it's not only beneficial, but I would say it's a necessity. Because you have readings on a second every second, and then you quickly get into difficulties with the TX duty cycle limitations in Europe. And I would say that RIM itself is a mesh technology, but the RIM technology can very much also be used in a star network configuration, so that the devices will connect directly to the gateway, or what we call board router. So even though we talk about this as a mesh network technology, it can handle many direct connections and operate also like a star network.
So I guess what's more for the residential use case is more that the fact that you want to have some sort of app on your phone monitoring things, and you want kind of responsiveness. So meaning if you turn off the water heater or stop the electric charging, maybe you want to go in and check on your app afterwards that the energy consumption has come down. So you want some sort of responsiveness, and it's kind of small network. So I think they're much more focused on this user experience latency things than the big network. The big networks are more system. They're made for systems, while the small networks is made for humans. So you have to take that into mind as well. There's another question. High power, low power devices couldn't mix. Is that correct? I also missed because of bad sound, the range in open field. Okay. Yes, the high power, we don't recommend to mix the high power devices and low power devices, because the reason is simply that if you have one low power device sending out 14 dBm and one high power device sending out 27 dBm, then obviously the low power device can maybe sometimes hear the high power device, but not vice versa. So that's the problem, that the low power device say, hey, I can hear this device very good, so I will have a connection with this device. So of course the mesh is dynamic and autonomous. So devices will choose the path that with the devices they can which they can hear very well. So obviously, if you have a high power device, a low power device can hear that, and he chooses to have a communication with that, but the link back is very poor. So that's the problem you get in mixing these, that you get asymmetric links, and somebody is choosing if we should use this link or not, and that can be then taking the wrong decisions. So that's why we haven't really, it's more recommended because we haven't really tested it in large scale, how this asymmetric links will make the system works. But we do see that it's a potential that it will create a bit unstable network, basically. Okay, the range in open field, first I said 1500 meter, but then I corrected myself and said that if this is out on the countries, we have in a city, we have seen that 1500 meter is the maximum range based on the background noise. But if you go out of the city on a deserted place, which often these solar panels, utility scale solar panels are, they are not in the city. They are typically out in a rural area. Then the background noise could be 10 to maybe 20 dB lower, which will triple the range typically.
I was just thinking about one more aspect of Vasili's question here, and Ørjan, you know, you say that there is not such a good idea to mix high power and low power, but how is it if the gateway or board router, the central device, use a longer, a more high gain antenna, and the other devices in the network use a smaller antenna because, you know, maybe you want to have a big antenna on the gateway? Yeah. How would that be done? Is that okay?
Yeah, that will not make an asymmetric link because the antenna gain is used both in reception and transmission. So if you have a 5 dB gain antenna on one side and a 0 dB gain antenna on the other side, it will still be a symmetrical link in terms of the link budget. So that's no problem. So this will also say about examples for directional antenna. For home use, I don't want to disturb others. I'm supposed to make my own gateway. Yes, you can make your gateway with a Wi-Fi module and the RIM module, so you can use that to connect to your Wi-Fi network and thereby also communicating to your phone and stuff like that. So that's possible. And directional antennas, yes, that is possible. I guess there's a lot of theory out on the internet about that, but I don't think you will, because of this frequency hopping, I don't really think you will disturb your neighbors anyway. Yeah, so yeah, of course, a high dB antenna is big. Maybe just, but again, I think Fritjof was talking about utility scale, and then big isn't that a big problem. Of course, in the residential area, big antennas are not do not have a Wi-Fi approval factor. So obviously you want smaller antennas, but yeah, you of course you can use directional antenna. That will not be an issue. Okay, so I think we are used our time here. So it was quite a few good questions. So thank you for that. We are. If you want to know more about our RIM technology, you can look at our webpage, Radiocrafts Technologies RIM Technology Overview. If you want to know more about how our wireless solution can benefit your solar energy systems, you can also contact us at sales.radiocrafts.com to have discussions on how our technology could be used together with your system to make an even better system. So thank you all for listening, and I guess have a nice day.
Yeah, bye-bye.
Bye-bye.